Howdy everyone, my name is Sabine Waldron and I'm from Texas A&M University. Today I'll be discussing alternative end conditions to characterize compressive strength of ultra-high performance concrete. So to begin, what is ultra-high performance concrete? UHPC is commonly used in bridge decks and overlays. The applications for this are because UHPC has a very low water to binder ratio, and so this causes it to have a very low porosity. When used in a bridge overlay, this means that water and salt from a salt truck can only penetrate so far from the surface, and therefore rebar or steel reinforcement is less likely to get corroded. And so the maintenance cost over time is significantly decreased compared to normal strength concrete. And the cool thing about UHPC is that the compressive strength is around 22 KSI, whereas normal strength concrete is between 4 to 2 KSI. And the composition of UHPC is water, binder, and steel fiber, hence with no coarse aggregate, hence the low porosity. And so what was the why behind this project? Well, currently ASTM C1856 requires that all UHPC cylinders be grinded at the end condition. So on the right-hand side, you can see the grinding machine, which we have at our lab. And in the center photo, you can see the grinded end condition after we demolded and treated the cylinder. On the left, you can see a raw end cylinder with no end treatment present. This process is very expensive, and it also requires a trained technician. And so we wanted to experiment and see, is there another solution to make UHPC testing more accessible? And so the research motivations began with a friend of ours, Dr. Tavares, and he wanted to see if these neoprene pads could be used to simulate the grinded conditions of the cylinders. And so he began with commercially available pads. On the top, you can see the 70A pad, and this is based on the durometer hardness scale. This pad is relatively soft. So in the center top photo, you can see evidence of confinement. And the pad is essentially destroyed after testing. So he thought, let's use a harder pad. On the bottom, you can see a fabricated 90A pad, and there's no evidence of confinement, and their pad is still intact after testing. And so the questions that we had going into this research were, can an alternative end specimen condition be comparable to the fixed and grinded condition? What is the optimal hardness and thickness of a neoprene pad to be used between steel caps? And how does the use of the neoprene pad affect the end condition of the cylinder? And does the number of reuses of the pad affect the results? And so the materials which we used were proprietary mixes from ductile UHPC manufacturers, Ductile, Cientech, and Steelite. And our mix distribution composed of 8 early age mixes with 2 super early age, I'd like to say, and then 10 later age mixes, which is 28 day or greater. In total, we casted and tested over 800 cylinders. A lot of work. The variables which we changed within this experiment were the end condition of the cylinder. So if we grinded it, if we saw trimmed it, or if we left it raw. We changed the thickness of the pad between 3/16 and 1/4 inch. And then we also changed the hardness of the pad. So earlier I showed the 70A, which is very soft. 75D in this case, represents a very stiff pad. We tested 90A, which is the softest pad in this case, and then the 75D, which is the hardest pad in this case. And this is all based on the durometer hardness scale. And so our test matrix looked a little like this. What I'd like to note is that for each end condition, pad thickness, and hardness, we tested about 3 cylinders initially. For example, raw end 90A and 1/4, or a saw trim 75D and 3/16. And we left 3 reserves to see what the ideal condition was, or which value or which end condition matched the fixed and grinded state. And we could compile more data points for the ideal condition in that test. But what we found is that the 75D pads were severely underestimating the fixed and grinded results. So this resulted in us changing our test matrix, and so we were able to have about 4 cylinders per test later on. I'll speak on this more though. And so this is the compilation of our data. I know it's a lot to look at, but note that the specimen age is in days, and the compressive strength is on the y-axis. We have saw trim and raw end cylinders, and we also have the variable pad thickness. And overall, we saw that the trend was, like I said, the 75D, seen in orange, severely underestimated the fixed and grinded result. And we believe this is because since the pad is so stiff it was creating localized pressure points along the surface of the cylinder. So for a raw end that had a lot of variability across the surface condition, it would cause premature fracture. But what we did find is that the 90 A316s and the 95 A316s resembled a fixed and grinded condition within around 10% for almost all cases. And we looked at the data a little bit more, and we found that for later age specimens that were around 22 KSI to 25 KSI, the 95 A316s could be a better solution than the 95 A316s, which is the softer pad. And for the very early age stuff, the 90 A316s was softer and could be better for the very early age testing. And so here's another plot that shows the percent difference with respect to the fixed and grinded condition. Anything that's positive is severely underestimating the results, and anything that's negative is overestimating the results. And as we can see here, the 75D is off the charts. I mean, it is above 30% with respect to fixed and grinded condition in almost all cases. And the thing I'd like to note, though, in the majority of our cases was the 90A through 16ths and the 95A through 16ths was almost always within 10% of the fixed and grinded condition. So this was proving our thoughts before. And so here are the same graphs, just excluding the 75D pads. And what I'd like to note here is everything that you see on the screen, 81% of this data seen on the screen in tests were within 10% of the fixed and grinded results. And 99% of the data was within 20% of the fixed and grinded results. And so here's a box and whisker plot, which shows the compressive strength in relation to the fixed and grinded condition. On the top x-axis, you can see the number of specimens we evaluated per test, so this ranged between 3 to 6 specimens. And on the bottom, you can see the specimen age in days, and on the y, you can see the compressive strength in KSI. And what I'd like to note here is that the box shows the inner quartile range. So this is the inner 50% of the data points. And for the 90 A316s and the 95 A316s, it almost always overlapped with some of the data of the fixed and grinded condition. So this enhanced our theory that maybe this could be a good solution instead of fixed and grinded. And what I said earlier is we wanted to characterize the end conditions and see how the concrete was interacting with the pad. And so we did this by using these Fuji films out of recommendation from Pratik Shah from Wishtani Elsner. We did this for when a UHPC cylinder was getting tested with pads. We had the steel cap, we had a film in between the steel pad to measure that interaction, and we had a film in between the pad and the concrete surface interaction. Likewise on the top. For the fixed and grinded condition, you can see on the right, there's no pads needed, so we just put the films right on top. And the results from this were really interesting. These pressure films had an associated scale range, as you can see on the left-hand side. So it was between 18.9 KSI and 43.5 KSI. And just by looking at the scan, we can see that we could estimate that the compressive strength was around 20 to 22 KSI. And here's the cylinder that was associated with this film scan. And this was taken from the top of the cylinder. And this was a saw trim cylinder, and you can see the 3D model that I was able to develop to show the end condition and how it was interacting with the film and with the pad. And so the pad showed a uniform distribution across the surface, which was very interesting. And on the right-hand side, you can see a cross-section that was taken from the point map on the film scan. And in the red dashed line, that is the value that we derived from testing, so around 21 KSI. And in the blue dashed line, that was the value given from the Fujifilm program, and that was the average of all the data points in that film scan, which is around 20 KSI. So the Fujifilm proved to be a very accurate representation when it was within the pressure scale range. And so here are some more models that showed the end distributions. On the left-hand side, you can see this is the fixed and grinded condition. All of these are within the same batch of that was casted. On the top center, you can see 90A and a quarter. On the right-hand side, these are all raw end, so 90A and a quarter. Bottom center, 90A 3/16. On the right corner, you can see 95A and a quarter, and then 95A 3/16. And what I'd like to note here is that the raw end shows a lot of variability across the surface, as expected. I mean, we didn't do anything to these end conditions. We just put them in there, put the cap on, let them cure. But interestingly, in the same batch, the saw trim cylinders showed a more uniform distribution, which showed us that the ends were able to be smoothed out, and the fixed and grinded condition, although it's still variable, we're still able to produce similar results in this case. And so another thing that we wanted to see was, can these pads be reused? In testing, for most of this data, we were just using one pad, and then we get another one and put it in there. And so we conducted some reuse tests, and we took a 95A 3/16 pad. In this case, all of the cylinders were salt trimmed. And we saw that over time, the pad was getting softer. So it was going from a 95A 3/16 pad to around an 86A, let's say. And so we thought, okay, if people wanted to use these pads in practice, maybe the 95A 3/16 could be a good solution for full later age specimens to be tested. And the softer the pad gets, it could be used for very early age specimens. And so here's the distribution for the raw ends 95A 3/16 pad. Of course, you can see more variability just due to the end conditions of the cylinder. And so the conclusions that we came to were the 95A 3/16 pad for saw trim and raw end cylinders, on average, provide the closest solution to the fixed and grinded condition for cylinders greater than 7 days. And we found that the 90A 3/16 pad for the saw trim cylinders only provide a reliable single-use solution for 3-day tests, so very, very early age tests. And we found that the 95A 3/16 pad for the saw trim and raw end could be used as a multi-use solution for very early age tests and later age tests. And overall, the saw trim and the raw end cylinders, the 95A and the 90A 3/16 pads received and achieved very, very similar results. And so I'd like to thank everybody who helped me in this research. First, my advisor, Dr. Kinsey Skillen, and the graduate students, Akan Hawk and Eleanor Garrett, and then the person who began this study, Dr. Tavares. Again, my name is Sabine Waldron, and I really appreciate you all taking the time to come out to this presentation today. Please let me know if you have any questions.